Okay, today we're doing day 4, and this is the real probability stuff. This is the real probability stuff, all right? So, up till now we were doing simulation. Now I'm going to get into the real foundational probability principles that we need to know. A lot of these you may have heard before. You may have heard them back in middle school when you did probability. You may have heard them a little bit in Algebra 2. And now we're going to really get into it. So the first thing we're going to talk about is called the law of large numbers. And this actually is something that we've been talking about all along. I've been kind of referencing it. So remember when we did our simulation, I said if we do one trial at a time, if that trial is an outlier, then it could be that we don't want to necessarily make generalizations about the population based on that one trial. And that's because maybe I was playing basketball and I had a bad day and I missed all my free throws. And now you're going to call me a 40% free throw shooter. You got to look at what I do in the long run, in the long haul. So over the course of my entire season, you really want to look at how I'm doing overall and kind of average out my free throw percentage. That's the concept of the law of large numbers. Basically, in the short run, when we have only a few trials, something like over here, when the sample size is small, we have an unpredictable probability. It's kind of all over the place. But in the long run, as the number of tosses increases, for example, if we're tossing a coin, the probability is going to become closer and closer and closer to what we would expect, like what it really should be. So example, let's say I'm tossing a coin. If I toss a coin 10 times, is it possible to get maybe like 8 heads? Is it possible? Yes. Is it likely? No. But is it possible? Yes. So maybe I would get the proportion of heads in that small sample size. Maybe I got 8 out of 10 heads, which is 0.8. In the short run, I could possibly have a probability of 0.8 for heads. Okay? But if I do this many, many times and I let the sample size approach infinity, then in the long run, the number of heads should even out and become closer to 50-50. Does that make sense? So let's try it one time. Take out your calculator, people who have the probability simulator. Remember, you're going to press apps and you're going to go down to prob sim. It's 0 for the people who have it. And then you would choose number 1, toss coins. And let's just toss a virtual coin 10 times and let's see what we get. Okay? So to hit toss, you would press the button above the toss, which is window. So here's one time. I'm going to spotlight heads. Okay, so everyone spotlight how many heads you obtain out of your 10 tosses. So then you're going to hit +1, which is above the window. And basically just keep tossing until you have 10 total tosses. Oh, 10 total tosses. How many times can you say that fast? 10 total tosses. All right. Once you have your result, then you're going to go over to heads by hitting the right arrow. Do you guys see that I got 6 heads out of 10? Number of heads out of 10 tosses. Is it possible to get 0 heads out of 10? Yeah, but unlikely, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 6 heads out of 10. Let's go around to the people who did this. What did you get? Here, let's take a vote. Who got 0 heads out of 10? Who got 1? Who got 2? Oh, you got 2. See, it's possible. Anyone else get 2? Who got 3? Who got 4? Who got 5? Oh, 1, 2, 3, 4, 5. Who got 6? Who got 7? 8? 9? 10. So you guys, basically it should be centered around 5 out of 10. The ideal, or the, basically we call this like the theoretical probability, should be 5 out of 10. It's what we predict will happen, right? But keep in mind, like it could possibly be that most of you got 6 out of 10. So it should be centered around here, but it is possible to get 2 out of 10 like Jasmine got. So going back to this now, this is basically what this is showing you. In the short run, probability is unpredictable. In the short run, probability outcomes are unpredictable. But in the long run, as the sample size n approaches infinity, this arrow means approaches, and infinity means like as we get more and more and more samples, the more samples we do, the probability should approach the theoretical. The experimental probability should approach the theoretical or ideal probability. This kind of goes the same for like the stock market. You guys know in the stock market day to day, we have bad things happen here and there. You know, there's a war, gas prices go up, people panic, people sell their stocks. You might have your stock go up and down. Picture that time plot on you guys' phones, right? So it's kind of jagged. But in the long run, it should either be steady, or if you have a good stock that's a good company, it should go up. Even though you might want to panic in the short run, overall it should go up and up and up and up and be a positive slope in the long run if it's a good company. Moving on, if you go to the next little page or slide, you're going to see some vocabulary words. Before we fill them out, we're going to go down underneath it to where it says, what is the sample space? A coin is flipped. So what are the possible outcomes when I just flip a single fair coin? Heads and tails, right? What are the possible outcomes when I roll a fair die, one single die? 1 to 6. So what I'm doing here is I'm listing out all the possible outcomes. These outcomes are called the sample space. It's just a list of all the possible outcomes. Now, a sample space is written the same way a solution set is written. It's written with those squiggly fancy brackets like this. And basically you just list inside of those brackets all the outcomes with commas connecting them. So flip a coin, heads and tails, roll a die, 1 through 6, etc. Okay? Now, here's where it gets a little bit more interesting. What if we do 2 events? So notice I'm using the word event. And the word event doesn't mean like we're going to a concert, we're going to a basketball game. It actually just means I'm doing 2 things that involve probability. So those events in this case are, I'm doing 2 things. I'm flipping a coin and I'm rolling a die. And I'm going to look at the combined sample space for those 2 outcomes, okay? So now, if I want to think about what the sample space is for that, one thing that I could do, because maybe I do want to list them all out. Anybody want to try to list them all out? What could I get when I do both things? Yep. You got it. So do you guys remember, thank you for doing that. Do you guys remember when we did The one where it had the treatments of like salinity and temperature or whatever. It's like a shrimp question. And I was telling you guys that you can either list them all out like this, and it's kind of annoying, or another thing that we can do, what did I tell you that we could do in order to obtain all the total number in this in the treatments, or in this case, the total number in the sample space? How many total outcomes were there in the sample space that he just listed? 12, right? So what do you think that I could do in order to figure out the total number of outcomes in my sample space if there's two events? How many outcomes are there for the coin? 2. How many outcomes are there for the die? 6. What can I do with the 2 and the 6 to get the combined sample space number of outcomes? Multiply. If you multiply 2 times 6, you're going to get the 12 total outcomes in the combined sample space. And that's going to be called the multiplication principle, which is, I think, on the next page, which we'll get there in a second. Okay. So I'm going to come back to probability model in a second. I'm going to come back to tree diagram in a second. Is multiplication principle anywhere? Do you guys see it anywhere? Boop, boop, boop. No, right? Okay. So it's okay. I'll just add it in here. So this, just label this the multiplication principle of probability, which basically says if you have two independent events, do you think that the coin influences the die or the die influences the coin? No, right? They're just separate. Then you can multiply them together to get the total number of outcomes. That says independent. Now the other piece that we have here is we can do what we call a tree diagram, because maybe in your head you couldn't list all those out. Maybe you just like it wasn't as obvious to you to list all those out. What we could do is a tree diagram. So a tree diagram you may have seen before, maybe back in the day, like Algebra 1, I think it was part of the curriculum. You basically make branches to represent the first event. So let's let the first event be flipping the coin. We could get heads or tails. So basically you write down what you could get on that first coin. You could just get heads or tails. That's the first branch. And then whether you get heads or tails, you're going to now roll a die. If you get heads, the outcomes on the die are still 1 to 6. Or if you get tails, the outcomes of the die are still 1 to 6. So you could either get heads on the coin or tails, but the die still would be 1 through 6. So once you make your tree diagram, basically what you could see is like this first column here is the first event. This is the first event, which is the coin flip. And then the second column here, that's your second event, which is the die roll. Once you make your tree diagram, you just count the total number of branches, and that's going to be the total number in your joint sample space. So do you see that if you count this, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total outcomes. And then you could easily just read off the branches like he just did when he listed them out. H1, H2, H3, H4, H5, H6. Tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. Okay? So now when I want to get into probability, you guys, probability is a fraction, right? So I haven't yet made a fraction out of this. So if I wanted to find the probability of getting heads and then a 1 on the die, I would have to know that I would have to take the fraction, and in the denominator I would put the total number of outcomes, which is 12, because there's 12 total branches. And then there's only one way to get heads and then a 1 on the die, right? There's just one branch here. So that would be 1 out of 12. And all these outcomes are equally likely because there's 12 total branches and one's not going to weigh more than another. Okay? But if I just asked you what's the probability of rolling a 1 on the die, do you guys see there's more than one way to roll a 1 on the die? You could either get heads and 1 or you could get tails and 1. So then you would put 2 out of 12, which is 1/6, which would make sense because when you roll a die, it's 1 out of 6, right? So basically the tree diagram is a nice visual way to represent your sample space. I want to go back to this where it says probability model. The probability model now is going to be the combination of two things. It's going to be the sample space, which is the list of all the outcomes, and then listing their corresponding probabilities. And usually we make it in the form of a table. Displays the sample space plus the corresponding probabilities. Okay. So let's say I wanted to make a probability model for the first one, 1A. The coin is flipped. The probability model will show the sample space, and then it will show the corresponding probabilities. So the sample space is heads or tails for a single coin. And then what's the probability of getting a heads on a coin? 1/2 or 0.5. And what's the probability of getting tails on a fair coin? 1/2 or 0.5. That's it. So the probability model is basically that's it. It just organizes all of our data together. It shows the sample space or the list of the outcomes on the first line and then the probabilities on the second line. And if it's a valid probability model, these outcomes have to add up to one whole or 100%. Okay? Does that make sense? So if we do 1B then, 1B is a single die is rolled. The sample space would be the outcomes on the single die, which are 1, 2, 3, 4, 5, and 6. And then the probabilities of those would be what? What's the probability of getting a 1 on a die? 1 out of 6. 2 on a die. 1 out of 6. They're all 1 out of 6, aren't they? And if we have a fair die, we call that equally likely, which means that all the sides are not weighted. They're all exactly the same. So when I add up these totals in the sample space, this should equal 6 out of 6 or 1 whole. That makes it a valid probability model. Okay? So now you have the foundation for some of the vocabulary that we need for this unit. We have sample space, which is a list of all the outcomes, and we have probability. Let's take it a little bit further. Next page. What if I flip 3 coins? Here's where it gets a little more interesting, right? So I have the first coin, I have the second coin, and I have the third coin. Okay, let's do this in 2 ways. Option number 1, multiplication principle. Before we get into this, Multiplication principle. How many outcomes on the first coin? On the first coin? 2. How many outcomes on the second coin? 2. How many outcomes on the third coin? 2. There's 3 coins, right? First coin, second coin, third coin. Multiplication principle says if we're doing 3 separate things that are independent, the 3 coins don't influence each other, right? Then we can multiply. And we're using the word and. And means multiply in probability. So what's 2 times 2 times 2? I'm flipping a coin and a coin and a coin. 2 times 2 times 2 is 8. 8 total outcomes for my coins. Okay. And now I could do this in the form of a tree diagram. Okay. First branch represents the first coin. What outcomes could I get on the first coin? Heads and tails. This is just the first coin. Now, no matter what happens on the second coin, if I got heads or tails, whatever, the next one's going to be still heads or tails, right? And now you draw branches again off of all these for the third coin. So basically, if you count up all my blue branches, how many total blue branches do we have? 8. And thus, now I can read across my sample space by just reading across my branches. So check it out. Do you guys see I could get heads, heads, heads? It's possible to get 3 heads, right? I could get heads, heads, tails. I could get heads, tails, heads. I could get heads, tails, tails. I could get tails, heads, heads. I could get tails, heads, tails. I could get tails, tails, heads. And I could get 3 tails. This is a list of 8 total outcomes. So the tree diagram is basically just a nice visual that displays it instead of you just trying to think of them all in your head, right? Okay, so now if I said to you, going back to the question says, what is the probability of getting 3 heads? Bye guys, have a good day. Do you now see that it's 1 branch out of 8? And that's the concept of probability.